Hello, today we're going to talk about rotational kinematics. You may recall some translational kinematics equation like the final velocity equals the initial velocity plus the acceleration times time. And then you had another one, the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the distance the particle would travel, and then you had the position of the particle equal the initial velocity plus 1/2 the acceleration times the time squared. So in rotational kinematics we have analogous equations. We have the rotational velocity, the final rotational velocity equals the initial rotational velocity plus the angular acceleration times the time, and the final rotational velocity squared equals the initial rotational velocity squared plus 2 times the angular acceleration times the angular displacement theta, and then you had the angular displacement equals the angular velocity times the time plus 1/2 the angular acceleration times the time squared. So you might see that we have analogous parameters, that the velocity corresponds to the angular velocity, the acceleration corresponds to the angular acceleration, and the position corresponds to the angular position. So here, just to clarify these parameters, that if you have something going around in a circle, here that's the angular displacement or position, and then you might imagine that this is a sweep hand of a clock or a wheel rotating, something like that. So this is rotating at an angular velocity omega, and this would be in degrees per second or radians per second, just like the angle is in degrees or radians. And then if this is speeding up, rotating faster and faster and faster, then it would have an angular acceleration, and that's the Greek letter alpha, and this would be in radians per second squared. So usually you want to work in radians, so that's a radian. The units of omega are radians per second, and the angular acceleration, the units of that are in radians per second squared. So just some examples of this. Here the Earth rotates at 360 degrees per day completely around, and then the Earth has zero angular acceleration, at least we hope it does. It's not speeding up or slowing down. Actually, I guess the Earth is minutely slowing down with time due to the moon's gravitational pull on it. But for most practical purpose, the angular acceleration of the Earth is 0. If this were a bicycle wheel and you were coasting at constant velocity, omega would be a constant. It might just say go around at 10 revolutions per second. And then if you speed up, you start pedaling, then your wheel would have an angular acceleration. So here you have to apply a torque, such as pedaling, and that would tend to make your rotation go faster and faster and faster. So just some useful conversion factors. If you have theta equals 45 degrees, and you might recall if you want to convert that to radians, there's pi radians per 180 degrees. You might recall from trigonometry that radian is really a unitless dimension or unit. You could go back and refresh your memory on that. But anyway, 45 degrees is just pi over 4 radians then. And then, for example, you might have something going around at, say, 4,000 revolutions per minute. Like your car engine might have this angular speed. You might recall that's RPM, but for purposes of unit analysis, you want to write it like this, revolutions per minute, and then usually you want to convert revolutions to radians or degrees. But anyway, there's 2 pi radians per revolution. And then you want to convert the minutes to seconds. In 1 minute, there's 60 seconds. So then you might see that the units cancel. Minutes cancel with minutes, revolutions cancel with revolutions, and so you end up with radians per second. So this would be 8,000 pi over 60, and that the units would be radians per second. And then you could reduce this down or use your calculator. Divide by 10 and then divide by 2, so you get 400 pi over 3 radians per second. So you could divide the 400 pi out with your calculator, which we'll do next time.